Hello and welcome to this video on conditional branching, which is essentially doing different things depending on particular conditions. But first of all, we're going to talk a bit about blocks. So let's just get rid of this code we've been working with for a while here and start afresh. So a block is essentially just a section of code which is grouped together. And in C, we typically denote these with curly braces, like the body of our main function, where the curly braces denote a block which belongs to the particular function name main. Now we can also have blocks within blocks in C, so you can have a set of curly braces within a set of curly braces to define a grouped block of code within some other grouped block of code. And we can actually have blocks without any particular purpose either, so just some section of code which we've decided we want to group together into a block. As I've said, these are typically denoted by curly braces, and so we can actually just type some curly braces within the block that is our main function to define another block within this. And code within here is code within this nested block. Notice that I've actually put another level of indentation in here. Again, this is typically considered good formatting just to show that the code here is actually within this nested block and not just within the first block. So okay, sure Joe, we've put a block within a block. Great, that's fantastic. What is this useful for? Well, when we're talking about blocks without a particular purpose, our main advantage really comes with something called scope. And when we talk about scope in C, we're really talking about an area in which a certain set of name bindings are valid. And what do I mean by that? Well, if we type something like int yards here, like we had in our previous program, an integer variable called yards, because blocks have their own scope, so they have their own set of name bindings, this link from the name yards to this particular variable called yards is actually only valid within this block. It's not valid within the wider block. And so any names and symbols which you define inside a block cannot be accessed by those names outside of the block. So in this example, we can't just have a printf down here, which says, yeah, okay, printf our variable yards, because the compiler is going to complain at us. The name yards at this particular point does not refer to an integer variable like it does within this scope here, because we're in the wider scope. We're only one indented as opposed to the two indent here. And of course, we can try this. If we go ahead and compile this, we'll see, hey, we get an error, use of undeclared identifier yards. The compiler is saying, I don't know what yards means in this context. Similarly, if we define a variable called yards up here, and let's say we initialize this one to 5 and we initialize this one to 2, and well, try and take a guess at which one's going to get output, of course it's going to be the variable with the value 5, because actually at this point we cannot reference this variable. It's in a nested scope which we've exited out of. And so again, if we try and compile this and we run it, then we'll see that of course 5 is outputted instead of 2. Even though it may appear that our yards variable that's been initialized to 2 is closer to our printf line, we know that because the second yards variable is defined within a scope which our printf variable is not within, that we in fact reference the yards variable which was initialized to 5 instead. And the C language really does care about scope. So after this ending curly brace here, after this particular scope which belongs to this nested block that I've highlighted here ends, we cannot even guarantee that this yards variable still exists. And if we try and do something sneaky like keep the location of this variable around even though it's no longer in scope, we could be causing all manner of problems. Now it's worth noting that in C, nested blocks do inherit the scope of their parent blocks. So if let's just rename our variable here to A, and if we create a variable in here called B, and that's 2, then we can access A from within the nested block. Even though this scope is different from this parent scope, which is the body of our main function, we can still access our variable A because the nested scope can access stuff within its parent scopes. So this will compile and work just fine. Awesome, 5. But as we've discussed, parent scopes will not get stuff from their child scopes. So the stuff in this block here will not get the stuff from this scope here. And we've already tried this, but just to show you again, if we just paste this down here and we try to access this B variable, we're not going to be able to do it. We're going to get a compile time error. There we go. So let's go back to where we were. Now there's another situation here which we haven't actually discussed. What happens if we not only declare this variable out here called A, but in this new scope for this nested block that we've created, we actually also create a variable called A in here? Which one is going to get output? Because we know that this nested scope actually does have access to its parent scope, so we have access to the variable A, which is initialized to 5, but we've also declared and initialized a new variable, a new integer variable called A, which we've initialized to 2. Which one is going to get output? Are we going to get a compiler error, or what's going to happen? Well, let's try it. Let's compile, let's run, and we get 2 outputted. So it turns out that the way scope works in C is that the closest scope, or the local scope, takes precedence over any parent scopes, or the wider scope in general. So in this case, because the more local name bindings take precedence over any wider ones, this printf statement uses this particular A variable, which happens to be initialized to 2. And this situation is actually called variable shadowing, by the way. We say that this variable shadows A in the wider scope. So this particular variable a shadows this particular variable a. And generally this is discouraged because, as you can imagine, this causes confusion. If we have this variable 2 here and we actually comment this line out, then what we're going to see is that we're going to get the value 5. And this could be confusing because you might have expected this variable to be declared, but maybe for some reason it wasn't. And so you get 5. Well, actually we wanted to get this local version, and we wanted to get a compile time error maybe here. But instead we got 5, and this could cause all manner of problems in our program if we were expecting it to be this more local variable, which happens to be commented out. So generally variable shadowing is discouraged. Now, while we're talking about scope, I should probably mention that C99 section 6.2.1.4 also defines a difference between file scope and block scope. So file scope is essentially the scope of things defined outside of any blocks, accessible throughout the whole file, whereas block scope is the scope inside blocks. So actually variables inside both our main function and inside our nested block here belong to block scope things, even though they're in different block scopes. But if we define a variable, say, out here, which I haven't even said we can do necessarily, but it turns out we can, this particular variable is defined in file scope. And hey, actually, if we initialize this too, then we have a lot of shadowing going on. We have this variable here, which is shadowing this variable here, and this variable here is shadowing this variable here. Again, variable shadowing can get confusing. Sometimes we refer to file scope as global scope because things declared in global scope are accessible anywhere throughout our file. And sometimes we refer to block scope, or particularly the closest block scope to a particular line, as local scope. So you may have heard me say that to this particular printf statement, this variable a is in the local scope, by which I mean it's in the closest scope. You can really think about scopes creating this huge tree. So at the top of the tree you have file scope, you have this big global scope, and then that may have scopes within it, and then those may have scopes within them, and so on and so on. But anyway, that's quite enough about scope for now. If we just get rid of this, and let's get rid of our nested scope just for now. Let's talk a little bit about conditions, so then we combine our knowledge of conditions with our knowledge of blocks to really get into conditional branching, which is the point of this video. So a useful case of blocks with a particular purpose are in conditional statements, which choose a particular block of code to execute depending on a particular condition. Now when we talk about conditions in C, we really talk about zero and non-zero values. So if you're familiar with the idea of a Boolean, a true or false value, in C, 0 represents false, something that is not true, and any non-zero value represents true, something that's not false. And if we want, we actually can just use numeric values as conditions in C, and that works fine, and we'll demonstrate that in just a second. But the most common way you're going to create conditions is through the use of conditional operators. So if I just create a multi-line comment here just to show these to you before we really get into using them, the operators are as follows. You have equals equals, which is the equality operator. So A equals B performs the test to see if the value at A is equal to the value at B. We have exclamation mark equals or does not equal. So if A exclamation mark equals B, then A does not equal B. The value at A does not equal the value at B. We also have greater than and less than, as you might expect. So we have A greater than B, A is less than B. So again, if the value at A is greater than the value of B, this one's going to be true. Or if the value at A is less than the value of B, this one's going to be true. We also have greater than or equal and less than or equal, which work as you might expect. And that's about it. And all of these operators yield, so result in 0 or 1 values. 1 if the comparison is true, because 1 is a non-zero value, as we've discussed, and 0 if the comparison is false. And this is outlined in C99 section 6.5.9. So just to give you a quick example of this, if we just get rid of this comment for a second, let's try the equality operator. And beware, by the way, a lot of people mix up the equality operator, which is equals, with the assignment operator, which is equals. If you're using this second one, you're setting the first value to the second value, or if you're using this first one, you're checking whether the first value is equal to the second value. These do very different things, and you can see why we might need two operators to differentiate between these two. So if we create two variables, int a equals 5, int b equals 2, so we've declared an integer variable a and initialized it to 5, and declared an integer variable b and initialized it to 2. And actually there's a shorthand for this, which we may as well use. You can actually just like comma separate this here, so if we did it like this, this would declare the integer variable a and the integer variable b, and we can actually initialize them just 2, so like that. And that works as you'd expect. It declares the integer variable a and initializes it to 5, and declares the integer variable b and initializes it to 2. Just a little shorthand which you can use. And now let's go ahead and do a printf, and let's printf the value a equals b. Again, note a equals b is a totally different thing. So what we'd expect here, because the value at A does not equal the value at B, 5 does not equal 2, we would expect to get the value 0 outputted. So let's check that. If we just compile and run, and excellent, we get 0 outputted as we would expect. And if we go back and we change this, so actually both values are initialized to 5, we should see that we get 1 outputted. And we do, excellent. And again, just to really reinforce this, if we get this back to being 2 and we used equals, so oops, we used the assignment operator, the single equals, rather than the equality operator, the double equals, and we compile and run this, then you'll see we get 2 outputted. Because actually what happens is we're assigning the value at B, which is 2, to the value at A. The value this gives us back happens to be the value that got assigned, which is 2, and so we get 2 back. So this could be used as a condition value. Because any non-zero value represents true, 2 represents true. So if we were to use that as a condition, it would work and we wouldn't get a compile time error, but it's probably not what we wanted here. We probably wanted to use the equality operator. So let's go back and use that again. Okay, so we know how to formulate conditions, we know how to create blocks, let's do conditional branching. The most basic way to do this is to use what's called an if statement. These are defined in C99 section 6.8.4.1, and essentially you write the if keyword along with a condition, and then you specify a block, and that block gets executed if the condition that you specified is true. So let's test this out. Let's write the if keyword, and then in brackets we type our condition. So let's say A equals B, let's use that again, and then we specify a block. So in here, let's just type a printf A equals B. So let's output the text A equals B if indeed A does equal B, if the value at A equals the value at B. In this case, we've actually verified this. We know that A equals B returns the value 0 because 5 does not equal 2, and so we expect this block to get entirely skipped, and so our printf should not get executed. Let's just test this is the case, and indeed we get nothing printed to our screen. If we just go ahead and we change this to a does not equal, well, 5 does not equal 2, so we'd expect that printf to execute. Let's compile, let's run, and hey, it works. And there are actually some more things we can do here as well. So linking to a particular if, you can have what's called an else statement. So if we write the else keyword and specify another block, and let's actually just change the text we output because that's slightly confusing there. We outputted the text A equals B even though we were doing it on the condition that A does not equal B. So let's just type condition is true, and we'll copy that line, and condition is false. And the deal with an else statement, as I've just implied with that text there, is that if we do not meet this condition in the if statement, then we go, okay, well we've skipped this block, instead let's do the else thing and let's execute this block. So if we change this condition back to equals and save, we would expect the condition to be evaluated. Well, 5 equals 2 is false, so we're going to get a 0 back, which means that this first block is going to be skipped, and we're going to execute this second block because of our else statement linked to the first if statement. And let's compile that, let's run, and condition is false, it worked. And it turns out there's actually even more we can do with this. So let's change our condition. Let's just use one of the other operators. Let's say greater than or equal to, why not? So if A is greater than or equal to B, well, 5 is greater than or equal to 2, so that should actually work. Maybe let's use less than or equal to then. And let's change the text here just to say something like branch A, and we can use this, and let's just say this is branch C for now. Well, there's actually something else we can put in the middle here. What if we say, okay, sure, we don't want this particular condition, but we want to do something else, not only if this particular condition isn't true, but what if this isn't true, but some other condition is true? Well, we can use an else if. So let's add else if here, and there we go. So if we specify another condition, let's say, okay, well, what about if A isn't less than or equal to B? Well, actually, let's change this condition. Let's say it's A less than B. So what if A isn't less than B? Well, okay, so A is either greater than B or equal to B. What if we want to do different things in both those cases? Well, okay, we can say else if A is equal to B, then we'll do something else. Let's just call that branch B. Else, do branch C. So if A is less than B, this block is going to get executed. If A equals B, this block is going to get executed. Otherwise, this block is going to get executed. So what's going to happen in this particular case is, well, 5 less than 2, well, no, that's 0. So if 0, well, okay, we're going to skip this block. So let's try the next condition. Okay, A equals B, well, 5 equals 2, that's going to be 0, so we're going to skip branch B, so we're going to end up executing branch C, this block here. But if we change our numbers, so we have 5 and 5, then what's going to happen is, well, okay, 5 is less than 5, that's not true, so we skip this block. We then try our next condition. 5 equals 5, yes, that's true, so we're going to execute this block and skip the else. And let's just go through one more example. So if we have 3 and 5, okay, well, 3 less than 5, yes, that's true. So we're going to execute this particular block, and we're going to skip both these blocks here. And let's just try actually executing one of these. So let's say we're going to aim for branch B. So we've set them equal to the same value. We should get branch B output, and we compile and we run, and excellent, branch B is output. So, good, this is all good theory. And as I've said before, by the way, we can use numbers just as conditions. So I could say, well, okay, if 0, else branch C. Well, this is always going to output branch C. So if we compile and we run, branch C is always what we will get. And we can also use if 1 or if 5 or something like that. And because 5 is a non-zero value, this condition is always going to be true. So we're always going to execute this first block here and skip these last two. So we're always going to get branch A as the output for this. And excellent, that's true as well. Just wanted to show you that don't be scared of using numeric values as conditions. It's just a zero, non-zero thing. But let's go back to where we were. So let's actually try to do something a little bit interesting with this. Let's just get rid of all this and let's have a variable which we're calling income. And by the way, I'm just going to quickly mention that in versions of C prior to C99, you actually had to declare variables at the start of blocks like this. So you could say, okay, int income, int A, int B, like this. But you couldn't have something before this, like a printf of sorts, and then declare them. You had to declare them right at the start of the block. This is no longer true in C99 and onwards. You can declare variables anywhere, and they get registered in their scope when they're declared. But back to what we're doing, let's go back to that income variable. Let's create a program that accepts some income value and gives you a suggestion as to whether you're going to have to pay tax on that value or not. In England, which is where I live, the tax threshold is somewhere around £10,000. So if you earn more than £10,000, or I think it's something like 10,600 for this particular year I'm recording this, then you have to pay tax on stuff above that threshold. So what we're going to do is we're just going to have a basic conditional branch which says, okay, if they earn more than, let's just say, £10,000 per year, then, okay, we're just going to output you may have to pay tax. And if you earn less than £10,000 a year, we're going to say, okay, you don't have to pay any tax. And then, of course, this is going to use conditional branching. So first of all, let's prompt the user for their input. So enter your annual income. And then let's have our scanf. And as we've sort of discussed in past, scanf isn't perfect because we could have overflow issues. If some bazillionaire is trying to use this program, they may have their income overflow, so it actually says they don't have to pay tax, and this could be an issue. So scanf is not bulletproof, but we're using it just for now because it's very easy to use. So let's scanf, let's use %d. Again, we're going to use the ampersand and then income because we have to pass the location of our income variable so that scanf can assign a value to that variable. And then let's formulate our if statement. So if, and our condition here should probably be income is greater than, let's just say it is 10,000. And okay, so this is the block that's going to execute if that's true. Let's then also prepare our else statement. So if the income is less than or equal to 10,000, then this block here is going to get executed. And we can just write some printf statements in both of these to output some text to the user. So you may have to pay tax. And let's also have one down here. You probably don't have to pay tax. Or maybe we should add in England. And we should probably have a new line here too. Let's actually just copy paste this. You may have to pay tax in England. And let's specify our currency, so GBP. And let's also just make this int variable unsigned because I don't think anyone earns negative income annually. Well, actually, you could do, I guess. Whatever, we're going to assume people don't input negative values for now. Let's just hope people aren't losing money annually. So let's go back to our terminal here, and I'm going to compile, I'm going to run, and okay, enter your annual income. Well, I'm not sure what my real annual income is, but let's just put in like £15,000. And okay, you may have to pay tax in England. That's good to know. Thank you, program. If we rerun and we say, okay, £900, you probably don't have to pay tax in England. Okay, so we've used conditional branching for some real purpose. This is good. And of course, this kind of branching depending on particular values is insanely useful in real-world programs and is used all the time. And I recommend you go away after this video and you really do try and make something for yourself. Try and make something which is kind of useful to you that uses conditional branching in some way. And remember, you have your if, else if, and else to play with. And actually, I didn't mention this, but you can actually have multiple else ifs. So you could have if A, then perform this block, else if B, then perform this block, else if C, then perform this block, else if D, then perform this block, so on, so on, so on, and then you're going to have your else finally at the end. So really do try and make something because it's really going to help you scope out and figure out how much you know about the language and really get a feel for the language as a whole. So that is all I had to say for this video. I will see you next time.